Welcome back to Mrs. O'Graham's Maths. This is a worked solution video for some D&D resources. And so first of all, a thank you to D&D Resources for allowing me to use their materials in this way and create this resource for you. This one is a distributions paper. It's their practice external assessment number 2 for standard 91586. Now I have put a link to their website in the video description, and I strongly recommend that you order yourself a paper copy of these so you can work through them as practices for the real thing before you go into that external. Before we get stuck in, it's important to note that I do use the graphics calculator throughout on this one rather than the formula sheet and tables. You are assumed to have a graphics calculator for this external, and it makes it much easier to do these calculations and a lot less time consuming with one. So these solutions are entirely using the calculator. On with question 1, where we have a normal distribution. We're told that the mean, we've got a mean of 11.2 kgs. We've got a standard deviation of 1.8. Assuming that the distribution of the weights is normally distributed like this, find the proportion of these TVs that have a mean weight between 10.5 and 11.3. So let's mark on 10.5 and 11.3, something like this. Doesn't have to be accurate on your drawing, but I do recommend you draw a picture every single time so you can see what you're doing. We need the number that's between, or the proportion that's between 10.5 and 11.3. So we go over to the graphics calculator. We are going to our statistics menu, distributions, and then normal, and we're doing NCD. We're finding out the cumulative amount between two things. Now our lower limit is 10.5, the upper limit is 11.3, sigma is 1.8, and the mean mu is 11.2. And then we execute that, and we've got our proportion is 0.1735. To part B, we've got 80% of these TVs she can unpack without any problem. So the 80% that are the lightest, we're looking at as being this lightest 80%. So we have a 0.8 proportion in there. So for this one, we want the inverse normal. Since we are working out the value of x, rather than working out the proportion, we've got the proportion, we're working backwards to find the x value that gives that proportion. So again, in our stats menu, we just come out of there, we've got distributions, normal, we're going inverse normal, we have a tail on the left, we put the area in as 0.8, the sigma is 1.8, that hasn't changed, and the mean hasn't changed either, that's 11.2. So if we enter that in, we've got x is equal to 12.71. For part C, we don't know the mean and standard deviation, and we're going to need to work out both of those. So let's start with our normal distribution. We know there's some mean mu and some standard deviation sigma. This is for the time it takes her to set up the TV for display. So the probability that she takes less than 20 minutes is 0.23. So it's going to be on the left down here. We've got a 0.23, and that's for 20 minutes. The probability she takes more than 32 is 0.15. So up on the right here, we have a 0.15, and it's at 32 minutes. Now what we want to do is match that to z values. Now z is equal to x minus the mean over sigma, and we can use that little thing to be able to link between these two and work out the values of mu and sigma. Now the equivalent values on the z curve we can find using inverse normal. So to get a value of 0.23 on the z curve, z has a mean of 0 and a sigma of 1. So we go inverse normal. On the left, if we want an area of 0.23 with sigma as 1 and the mean is 0, that happens pressed the wrong one. Let's just go back there. Inverse normal. So that happens at minus 0.7388. So this value just here, minus 0.7388. Now for the 0.15 on the other end, let's just change that around. We've got a tail on the right. The area is 0.15. Mean and sigma haven't changed. That Z value is 1.0364. Now we map the X to the Z using this formula in between that matches the X values on the left with the Z values on the right. So on the left, where Z is a 20, where X is a 20, I should have said. So if we're using the Z equals X minus mu, we have our value of 20 minus mu over sigma is equal to minus 0.7388 of the Z value that we worked out here. That bit there is at the same bit as where the 20 is on the X. Similarly, we have where the 32 is over here matches with where this Z value is here. So when we have Z of 1.0364, we have a X value of 32 minus mu over sigma. Now we rearrange each of these into formats that we can put into the graphics calculator for simultaneous equations. So I've brought the sigma up and multiplied it and then add mu over to the other side. Then on this one, 1.0364 sigma plus the mu will be equal to 32. Now we can go to equation solver. We're doing simultaneous equations with two unknowns. The format we're looking for is just here. Of the two variables are equal to a constant, so that's why I wrote that down like that here with two variables and then equal to constant. So the first equation, we've got minus 0.7388, then a coefficient of 1, and it's equal to a constant of 20. The second equation, we've got 1.0364, coefficient of 1, and it's equal to 32. Now we hit solve. So the X was representing the sigma. So sigma is equal to 6.7, that's going to round up to 7.6, and the mean is equal to 24.99. And we're measuring in minutes. Now for part D, we've got two things that we want to see the chances of them happening at the same time. So the first one, so store A, the probability that the profit is between 45,000 and 50,000. We're going to pop that into our normal distribution calculator. So stats menu, distributions, normal, cumulative. Right, our lower limit is 45,000. Our upper limit is 50,000. Now for store A, we have the standard deviation is 6,550, and the mean is 52,500. Okay, so the probability of that one is 0.2253. Now let's do the same for store B. This probability will be, let's just go back one. This time our standard deviation is 72,000 and the mean is 44,000. So the probability of that one is 0.2424. The probability of them both happening is, think of your tree diagram. We would do store A, yes, store B, yes. Put those two probabilities on that we just found out, so we'd be timesing them together. So the probability of both 0.2253 times 0.2424. That comes to 0.0546. Now the assumptions that we've made, we have assumed that this is normally distributed because we haven't actually been told that in the question, but the information we've given has led us to believe it's normally distributed. And we will assume that the two of those are independent of each other so that we can multiply it through together to get this result for the probability. Now for the last part of this question, we are using what we just worked out in part I and another appropriate probability distribution to calculate the probability that profit from store B is between 45 and 50,000 in 2 of the next 3 years. Okay, so we have 3 possible years to choose from, and we want the probability that we get exactly 2. So this is a binomial distribution. So X is following a binomial distribution now where we have 3 trials, because it's 3 years that we're trying out, and the probability of success that store B is between 45 and 50,000 we worked out up here. So it's this this one here for store B, 0.2424. So we can put 0.2424 in for our probability. Now we want to work out the probability that X is equal to 2, so exactly 2 of the 3 years. Matches this criteria. So statistics, distribution. This time we're doing F5 for binomial distribution. We're doing BPD for exactly at a point. So that is F1. We need to tell the calculator our data is not sitting in a list that it has in its tables. It's actually a variable. So we need to change that to variable by hitting F2. Okay, now the X value is 2. We want X equals to 2. The number of trials is the 3 years that we've got, and the probability of success is 0.2424. Enter that, and we have a chance of 0.1335. Now we need to justify our choice of distribution, identify key parameters and assumptions. So binomial, because run through FIST in context. So there are a fixed number of trials, which is 3 years. Each year is independent of each other. The probability of success remains constant at 0.2424, and the outcome is either true or false. It's between the criteria that we've been given, or it's not. The key parameters were that n is equal to 3 and the probability of success was equal to 0.2424. And finally, the assumptions, we are assuming independence of each year. Also that the conditions don't change over time, so we don't get any changes in those probabilities over those 3 years. Okay, that's the end of question 1. Okay, for question 2, calculate the number of warranty claims Elisa can expect in any given week. So to do that, we're doing the expected value of W. So expected value of W is to do 0.78 times 0, 0.13 times 1, 0.06 times 2, 0.02 times 3, and 0.01 times 4. You can type that into your calculator or you can put it into your stats table. If we put all of the X values in here, and then all of the probabilities in list 2. Now we do the calculations on it. We're doing a 1 variable calculation. Oh, I need to change the settings first. So F6 for settings. We need to make sure that it knows that our things are in list 1 and their frequencies are in list 2. So their probabilities appear in list 2. Now I can do a one variable check, and we go down and we see that x bar is equal to 0.35. That is the mean, that is the expected value. So this is 0.35. It can save you a bit of time, especially if there's more that we have to work out later on. It's now already sitting there in the table. But if you don't like using the table, you can just type it into your normal menu. Okay, now explain the answer from part I in terms of the context of the question. So we are talking about the number of warranty claims Elisa, I'm not sure, receives per week on items previously sold in her electronics store. So she can expect an average of 0.35 per week. Now, since you can't get 0.35 of a claim being made, let's see if we can work out that in more whole numbers. So if we do 1 divided by 0.35, we can see how many weeks we would have to wait until we got a full claim. So approximately 3 weeks. So 2.85 would mean that we've got about 1 claim every 3 weeks. Part B, we want the probability that she receives no more than 2 warranty claims within a 4-week period. So if we've got 0.35 per week, we can times that by 4 to get the average number that we expect in a 4-week period. So lambda, because I'm going to go on and use Poisson in a moment, is equal to 1.4 claims in 4 weeks is the average. Now we can use Poisson because we're talking about an interval and how many things happen within that interval. So now we want, what's the probability that Eliza receives no more than 2? So that can be 2 or less. X less than or equal to 2 when lambda equals 4. So let's go to, 1.4. Stats menu, distribution. We're moving along to Poisson. We are doing cumulative because we are going less than or equal to 2. And we are entering a variable where x is 2 and the mean is 1.4. So we have a probability of 0.8335. Next, we need to justify our choice of using Poisson. So that's the acronym RIPS. R for random. All right, let's put that in a sentence. The claims occur randomly. I is for independent. P is for proportional. And S is for singly or not simultaneously. And finally, assumptions. Well, the second point really is an assumption. So we've assumed independence because there is a possibility that perhaps you had one batch of faulty things go out, that if one starts to break down, the others from the same batch are also more likely to break down. So there's a chance there, but we're assuming independence in this situation. Now Eliza makes this change, and the probability of going a week without claims is 90%. So the probability that x is equal to 0 is now 0.9, and we want to find out what the new lambda value is to make that true. So we're using inverse Poisson here. So if we know the probability that x is 0 is equal to 0.9, that's the same as e to the minus lambda is equal to 0.9. Now, if you don't like playing around with the algebra, we can go to equation solver here. So we pop in e to the negative lambda. Well, we don't have a key for lambda. I'm just going to use x is equal to 0.9 and solve. So lambda is 0.105. And that was per week. Now we want to work out the no more than 2 warranty claims per month thing. So if we times that by 4, we've got 0.10536 times 4. 0.4214 per 4 weeks, which we were told in the question to count a month as being 4 weeks. So we'll carry on with that. So now the probability that x is less than or equal to 2 with this new lambda, we'll go over to stats, distributions, move along to Poisson, cumulative up to and including 2 with a mean of a lambda of 1.4214, sorry, 0.4214. And the chance of that happening now is 0.9909. So she's got a 99% probability now of receiving 2 or less warranty calls per month. So a 1% chance of it going over the 2 warranty claims. So that's had a really good move towards what she was wanting, of being confident that this policy would have the effect of there being a very small chance of receiving more than 2 warranty claims per month. So the policy has had the desired effect. Now for question 3. Now the clue in this one is that we're being told about modal times. So that is almost always going to be the triangular distribution. We have a minimum, a maximum, and a mode. So that sets us up for a triangle. We've got a minimum at 2 minutes, a maximum at 20. So there's the base of our triangle. And our mode happens at 8. So there's the peak. So it's triangular because we know the minimum, maximum, and modal values. Now I have skipped ahead of myself just a little bit and drawn the picture already when it asks for it down here. So let's just pop that back in again. We have a terrible triangle from me. There we go. A little bit better now. We've got the peak at 8 and the minimum, maximum at 2 and 20. We need the height as well. So the height of that triangle, I'm going to actually do a different color. Now, height is always 2 over b minus a, so that's 2 over 20 minus 2, 2 over 18, or 1/9. Okay, now work out the probability that during the week she spent between 5 and 10 minutes serving a random customer. So looking for x being between 5 and 10. Now this will be, what I'm actually going to do is the 2 pieces of 5 and 10 separately because they sit on different sides of the 8. So if we go for, okay, let's color code this. So less than 5 being this triangle here. So the probability that x is less than 5 being that left-hand triangle that I just popped in there. That left-hand triangle has a base that's between 2 and 5, so it's got a base of 3. Now the bigger triangle up to the peak between 2 and 8, that would have a base of 6 and it's got a height of 1/9. So the smaller triangle is half as big as that. So instead of a base of 1/9, it's got, sorry, a height of 1/9, it's got a height of 1/18. So that area is now going to be half times 3 times 1/18, which is 1/12. This triangle over here that's 10 and above will do a similar thing. So we've got the triangle that goes 10 up to 20 has a base of 10. The right hand half, well not half, but you know, the right hand of the mode from 8 to 20, that has a base of 12. So the scale factor between them is to times it by 10/12. So if we do that with the height on the mode is 1/9. So if we do 1/9 times by 10 over 12, we will get the blue height as 5 over 54. So now the probability that x is more than 10 will be half times the base, which is 10, times by 5 over 54, which comes to 25 over 54. Okay, now we can carry on and work out this orange piece in between that we were trying to get originally. So the probability that x is between 5 and 10 will be 1 take off the pink piece and the blue piece. So that's 1 minus 1/12 and take off the 25 over 54. Oops, I have made an error. Let's try that again. Right, 1 take away the 12th and take away the 25 over 54 equals 49 over 108, or 0.4537. Just before I move on, you can do this using the formula sheet for triangular distribution to get the heights of those pieces that way. I just prefer to use similar triangles. Finally, we've got a distribution model of the number of sales through the website per day. So we've got number of sales along the bottom. We've got the probabilities up the side of getting that number of sales in a day. So use this data to complete the table below, which shows a probability distribution model for n, the number of sales per day. So let's just read off of the table. We're missing a value for 0 and 4. Now, just because I've zoomed in quite a bit, I can see there's the tiniest of gaps between 0.1 and the top of the bar for 0 there. Same for 4, but I think that is entirely unintentional. It's just the difficulty of getting the formatting to match the lines exactly on this one. And we can see from the answers that was intended to be 0.140, and this one here is 0.125 for 4. Now we're going to calculate the mean number of sales, so that's the expectation of n. And I'm going to take you through doing it on the table again, because I think this is going to save us a bit of time. Rather than going through and doing all of the multiplies of 8 different items, let's pop it into here. So our values now are 0 is 0.1, then we've got 0.15, 0.2, 0.25, 0.125, 0.1, 0.05, 0.025. Okay, now we are doing some calculations, so press F2. Check the settings, show that our list is in list 1 and our frequency is in list 2. That's still there from where we did it earlier. Okay, and now we're doing a 1 variable calculation, and here we have x bar. So expected value of n is 2.775. And that's an average, so it's okay to leave it as a decimal. The assumptions that we're making is that this pattern is going to hold true. So it's always between 0 and 7, and nothing's changing in the conditions of how customers are purchasing. Okay, Eliza has a goal to reduce the probability of 0 online sales down from 0.025 in any one 24-hour period or day. How many online purchases would she have to make to achieve this? So we want the probability that x equals 0 to become 0.025. Now this is a Poisson type of distribution because we're looking at the number of purchases in a time period. So if we're doing inverse Poisson to find out lambda, the average number of sales, then e to the minus lambda is got to be equal to 0.025, because that's the probability x equals 0 is e to the minus lambda. So let's solve that equation. We're doing equation solver. We have an inverse Poisson in here from earlier, so we just need to change the value in there. So that's going to be 0.025. So now lambda is equal to 3.69 sales per day on average. So now, is this a negative or a positive for her business? Let's take a look at what she was doing before. We had, at the moment, she's got an average of 2.8, and this is saying it would go up to 3.7. So that's a positive. And that brings us to the end of this practice external assessment from the D&D Resources. If you found that helpful, please like, subscribe, comment, whatever, interact with the video so that it helps other people to find it as well. And if you need more materials for this type of practice, I have a bunch more if you go to the homepage of my channel. All right, I will see you there. Bye-bye.